Hello and welcome to Biophysical Chemistry. My name is Umar, and today we'll be talking about problem 3.11 from the Atkins textbook. So this question asks us to calculate the change in molar Gibbs energy of carbon dioxide, which is treated as a perfect gas, at 20 degrees Celsius when its pressure is changed isothermally from 1.0 bar to A 2.0 bar and then B 0.00027 atms, which is its partial pressure in the air. So right off the bat, we can kind of see how there are two components to this problem, and I think that the easiest way to go about this is to first recognize what we're given in the problem and what we're not given, and we can use that to determine what equation we need. So we're asked to determine the molar Gibbs energy, so we're going to need a Gibbs expression within this equation somewhere, and we're given two pressures because we're shown that there's a isothermal change from, at least for part one, from here to here, and we're given our temperature here, which is 20 degrees Celsius. So that's what we're given here. And so before we move forward, I think it's important to just really quickly convert our temperature from Celsius to Kelvins. It's a very simple step, but often it's easily missed and it results in getting the wrong answer. So let's just take care of that right now. And so I'm sure, as you know, to convert to to convert to Kelvin, you would need to simply add 273 degrees. So simply going to be 273 plus 20 is going to get us 293 degrees Kelvin. And that's our temperature for this problem. And so now let's look at what else we were given. We were given two pressures, P1 and P2, and we have our temperature, and we need to find the molar Gibbs energy. And so the best expression to use here is this equation right here. And it is delta G, which is what we're going to be solving for, equals RT, and the natural log of P2 over P1. And so R here is just simply our ideal gas constant, which is 8.314. T is the temperature we just found, 293. And then we have the natural log of P2 over P1, which over here, P2 is 2 bar right over here, and P1 is 1 bar right over here. So it's just going to be 2 over 1. And so from here on out, it's a really straightforward calculation. And so let's go ahead and plug that into our calculator. And what I got was 1688.51 joules per mole. You can convert this into kilojoules as well if you'd like. For now, I'm going to leave this in joules. And so that's our answer for part A. And now let's look at part B. So now it asks us to determine the change in molar Gibbs energy once again when the pressure is changed isothermally from 1 bar to 0.00027 atms. And so one part of this that might catch you off guard is the fact that now we have different units between our pressures. So it's going to be the same exact equation again because we have the same knowns and unknowns. And so that part of it's very straightforward. And this part of it is too, because this conversion really isn't as bad as you'd think. Because the conversion of ATM to bar is simply this. Let's write part B right here real quick. So 1 ATM is equal to 1.01325 bar. And so as you can see, this is very, very, very close. And for this problem, this difference is pretty much negligible. So we can basically just keep the same value that we had up here. So this is going to be 2.7 times 10 in the negative 4. And we're going to use that as our P2. Very straightforward. And so now we can plug that back into this equation that we used right over here. And let's go ahead and do that right now. So again, delta G is our unknown. We have our ideal gas constant, our temperature, which is still 293, natural log of P2, which is now going to be 2.7 times 10 to the negative 4 over 1, which is our P1, just like last time. That's all that's changed. And so again, this is going to be a very straightforward calculation from here. And let's plug this into our calculator. And the answer that I get here is negative 19,904.0 joules per mole. And so you can convert this into negative 20 kilojoules as well. But I'm going to leave this in joules for now. Joules per mole for now. And so as you can see, once we kind of figure out what's missing, what we need to solve for, and what we're given, and we determine what equation we need, the calculation is very straightforward. And so my advice would be for problems like this, just kind of go through that method of finding what you're given, what you're not, and use that to determine what equation you need, and it'll be very straightforward from there. And so I hope this was helpful. Thank you for watching.